This is section 11.3. We're going to talk about area of regular polygons. So we do have to remember that regular polygons are polygons that are equilateral and equiangular. So just that's something to keep in mind. So if we imagine a polygon inscribed in a circle, meaning every vertex of the polygon is touching the circle, then the center of the circle, C, would also be the center of the polygon. So regular polygons can have a center, and they also can have a radius. So a radius of the circle, like CA and CB, could also be a radius of the polygon if it goes to one of the vertices of the polygon, to one of the corners of the polygon. An apothem, which is our new segment, like CD, is not in a circle. It only exists in a polygon, and it's perpendicular to the middle of the side of the polygon. So it goes to the midpoint of the side at a right angle from the center. So for our example / first check-in, we'll do this whole one together. We're going to identify each part of the diagram. So there are 4 different radii drawn in this picture. We're going to name one of them. So anything from the center to one of the corners is a radius, like segment AB. The other options could have been AI, AF, and AE. The center of the polygon would be that point A. The apothem has to go from the center to a right angle on the side. So the only one drawn here would be A to J. And then a side of the polygon, since this is an octagon, there's 8 possible answers. So we could say CB, BI, IH, HG, GF, FE, DE, CD. So let's start with CB. A central angle is exactly what it sounds like. It's an angle at the center, and it's made with 2 consecutive radii, and by consecutive we means we don't like skip over one. We don't connect C to here and C to A and then just have one big one. It's going to be between 2 consecutive radii of a regular polygon. So in our picture, angle ACB would be a central angle. And since the polygons are equilateral and equiangular, the central angles are also all equal. So to find one of them, we would do 360 divided by the number of sides. So n is always going to represent the number of sides that our polygon has. So for example, number 2, we want to find the measure of the central angle of a pentagon. Well, that is when n is 5. So we would do 360 divided by 5. And we get 72 degrees. For a dodecagon, n would be 12. So we would do 360 divided by 12. So the central angle would be 30 degrees. So here's a check-in for you to try. You can pause. Answers are posted on Google Classroom. So the real part of this lesson is the area of a polygon. And our formula is going to be A equals 1/2 times N times A times S, or as I like to say, 1/2 NAS. So we're going to 1/2 NAS our problems. N is still the number of sides. A is the length of the apothem, and S is the side length. To start every problem, we will sometimes have a picture, but maybe we won't. But we're going to create the little right triangle that exists inside when we connect the apothem to half of the side, and we use a radius. So that's the little triangle I've drawn here. So this is the apothem, this is the radius, and this is half of the side. I'm going to write that as 0.5 S. The angle at the top here is going to be half of a central angle, because essentially the central angle would have been if I connected 2 radii, and it would have been this big part, but I'm only using half of it in my triangle. So if a central angle was 360 over n, half of it is 360 over 2n. And this triangle is going to be the one we set up every time. Likely in our class, we will not have to worry about the radius ever. We're either going to be given the apothem and we will have to use that to find the side, or we'll be given the side and we're going to have to use that to find the apothem. We're going to ignore the problems that have a radius in them. But this triangle should be the very first thing that we're setting up when we list what our N, A, and S are. So example 3A says find the length of the apothem of a regular pentagon with a side length of 8 inches. Then find the area of the pentagon. So the N for a pentagon, the number of sides is 5. We don't know the length of the apothem. It says find the length of the apothem. So A currently is blank, and a side length of 8 inches. So S is 8. Let's make our little triangle. We're going to ignore the R. We don't know A, so that'll be a variable for right now. The bottom is half of S, so half of 8 is 4. And my angle is 360 divided by double the number of sides, and the number of sides was 5. So 360 over double 5 is 360 over 10. That's going to be 36 degrees. And now we get to go back and use SOHCAHTOA to find out what the A is. Because the angle is always going to be in the same place, this side's always going to be O, this side's always going to be A, we're always going to use tangent for these. We're not going to have to guess which one we're using. Tangent 36 equals, and it's O over A, so that's 4 over A. And because the 4 is in the numerator, we're going to divide 4 over the tangent of 36. I get 5.5. So that's my apothem length. And now I still have to find the area of the polygon. So we're going to 1/2 NAS. I have a list of NAS, so those are just going to go right into my formula as it is. And I'm going to type this all into my calculator. I'm going to do a 0.5 times 5 times 5.5 times 8. And my area was 110, and if my units were inches, we're going to say inches squared. All right, another one of those together. So example 3B, find the length of the apothem of the regular heptagon with a side length of 20 centimeters, then find the area of the heptagon. So N for a heptagon is 7, and if we weren't sure, we could count the number of sides. A is blank because it says find the length of the apothem, and it says side length of 20 centimeters, so S is 20. When we make our right triangle, we don't know the apothem, so that's my A. This side is half of S, so half of 20 is 10. And my angle, which will be 360 divided by double the 7, 360 divided by 14, is going to be a decimal. It's going to be 25.7. And that's okay. We can use decimal degrees. We said we're always going to use tangent. So tangent of 25.7 equals over A is 10 over A. So we'll do division, 10 divided by tangent of 25.7. And I get 20.8. And now for our area, 1/2 NAS is 1/2 times our list, 7 times 20.8 times 20. So on my calculator, I would do 0.5 times 7 times 20.8 times 20. And I got 1456 square centimeters. So here's one for you to try. You could pause. Answers are posted on Google Classroom. For example, 4a, find the length of the side of the regular octagon with an apothem of 8 inches. Then find the area of the octagon. So n for an octagon, number of sides is 8, and the apothem length is 8. We want to find the length of the sides. We don't know s right now. When I make my right triangle, I now put 8 on the side where the a goes. And the bottom, since we don't know it, we don't know s, is going to be 0.5s. We angle 360 over double the number of sides, so 360 over 16 will give me 22.5 degrees. Once again, we're going to use tangent. So tangent 22.5 equals O over A, 0.5s over 8. So the variables on top, the numbers on the bottom, we're going to do multiplication. But instead of just saying s equals, it's going to be 0.5s equals 8 times tangent 22.5. So when I do 8 times tangent 22.5, I get 3.31 or 3.3. And I still have to divide here by 0.5 to get s alone. So my s is really 6.6. So now for my area, my 1/2 mass, my list is 8, 8, and 6.6. So I get 211.2. And this was inches, so inches squared. One more together. Example 4b, find the length of the side of the regular hexagon. We're going to plot them to 15 inches, then find the area of the hexagon. So for a hexagon n, the number of sides is 6, and we were told the apothem, the A, is 15. I'm going to make my right triangle. 15 goes on the side where A is. We don't know the side length, so the bottom will be 0.5s. And my angle will be 360 over double the 6, so 360 over 12, 30 degrees. So tangent 30 equals 0.5s over 15. So it's going to be 0.5s equals 15 times the tangent of 30. So that's 0.5s equals 8.7. And when we divide by 0.5, s is 17.3. And then the last thing would be to do 1/2 mass. See our full list. So 1/2 times 6 times 15 times 17.3. And I get 778.5. That was inches, so inches squared. So here's the last check-in for you to try. That's it for section 11.3, finding the area of a regular polygon.